I see our final speaker. Once again, I'm happy to reintroduce Yingte, who's going to be talking about automating equational proofs in Dirac notation. So please go right ahead.
Okay, this time I hope you hear me clearly. I thought I would lose this chance, but they fixed the issue in the last minute. That was dramatic. Okay, our work is about Dirac notation. And what is Dirac notation? Here are some examples. In 1939, Paul Dirac proposed his notation to express linear algebra formulae in a compact and convenient way. And we know that quantum states live in Hilbert spaces. So Dirac notation soon become the working language for quantum mechanics, quantum computation, and quantum information. And we use bra and ket to represent the vectors in Hilbert space and the dual space. We also use the scalar and operator, linear operator in our notation. For example, here the first expression represents the superposition state for a qubit system. And in general, the language itself is quite free and casual, sometimes ambiguous. And the valid transformation depends on the reasoning of its semantics. And moreover, we can give the matrix interpretation to its meaning. For example, the basis 0 and basis 1 of the qubit system can be represented by column vectors, and the results of inner product and outer product are represented by this and calculated in the matrix way. So here is an example of a quantum information lemma that is expressed as an equation. Assume we have two subsystems. They are in the Hilbert space of HV, and they are in the maximally entangled state. And assume we have an operator M, which is in HV. And the fact is, if you apply M on the first subsystem, the result is equivalent to applying the transpose of M on the second subsystem, no matter how the two subsystems are separated. So how do we prove it? By equational reasoning. The left-hand side is transformed in this way. We unfold the definition and push terms into the sum. This is by the bilinearity of the product. And we rearrange the tensor and composition. Sometimes we need to insert the identity operator of identity matrix into the formula. So the right-hand side will be transformed into the same syntax using similar approach, so the equivalence is acknowledged. Such reasonings appear everywhere. For example, in theorem prover, you have to manually prove this. For example, in the verification of quantum programs. So an important question is, can we automate this procedure? So here is an analogy for the problem. The structure of the equivalence for Dirac notation is like a labyrinth, and finding the proof for the equivalence is like finding the solution trace. And our work aims to provide the guidance, or in another word, the understanding of the structure that can help to select the direction during proof. So the first step is to formally define what is Dirac notation. We work in universal algebra framework where we have a signature of function symbols, and each function symbols have their fixed arity. And we have a set of variables, and basic concepts like substitution of variable and pattern matching are also defined. So here is our core language for Dirac notation. Core language means we don't consider a big operator sum that appears as in early examples. And we have 5 sorts. They are bases, scalars, ket, bra, and operator. Take ket as an example. It can be variable x or 0 symbol or the basis ket, or it can be the adjoint of a bra, or it can be scaling, addition, an operator ket multiplication or tensor product. One thing to note is it is a little bit different from the original casual Dirac notation, where we don't have separated symbols for different kinds of terms. Here we separate the symbols, meaning we have 3 multiplications. This is done deliberately because we want to disambiguate them, and we also relate our syntax with the common understanding of Dirac notation. So this is done by notational semantics, which maps the syntax to its interpretation as set theoretical objects. For example, when we want to calculate the semantics of the tensor product of kets, we first calculate the semantics of K1 and K2 separately, and they are the vectors in the Hilbert space in the mathematical sense. And the whole denotational semantics is taken as the tensor product of the 2 vectors. So we have the formal language, and this is how we human understand and reason about equivalence. But computer cannot do it in this way. What we need is a formal proof system. So we further on explore how we use equational logic to do this. Equational logic defines an equational relation that is compatible with substitution and term construction. And the substitution and construction are the elements or the language in universal algebra. And this is essentially the common sense, the formalization of the common sense of equivalence in algebra. And we have more axioms besides this in this logic to describe the language, the behavior of the language. These are the axioms for linear space, and we have more for other structures like tensor product and inner product. One thing to note is the denotational semantics can be considered as a model for the logic system, meaning if we prove that 2 terms are equivalent in using the logic, then their interpretation should be equivalent. This is what we want because we want to. Our goal is to prove the equivalence according to their interpretations. But the other way does not hold. So there are some equivalence that holds in denotational semantics, but they cannot be captured by these axioms. So the logic itself cannot be complete. And we can also consider how hard is a problem. We can provide 2 ways of thinking. One is if you have the concrete basis, meaning that you can do the decomposition, then you can reduce the equivalence problem of Dirac notation to the theory of reals, which is decidable. And essentially, this is transforming the variables into their matrix interpretation and do the calculation. But this is impractical because the complexity depends on the dimension of Hilbert space, which can be quite high. And this is exactly why quantum computation cannot be efficiently simulated using classical computers. And another observation is because we have the set of equations as axioms. So if 2 terms are provable equivalent, then the writing trace can always be searched out. But again, this is not practical. So what is a practical way? We use the term writing as our technique. In general, term writing decides equivalence by normalizing the 2 terms and see whether the results have the same syntax. The normalization procedure is powered by matching and replacing using a set of rules. We use the special variant of term writing called AC term writing. And AC means we have associativity and commutativity in our axioms, and they cannot be decided using right rules. So they are lifted to the meta level, to the syntax level, and they are considered during matching and the checking of syntactical equivalence. So these are our rules, and many of them are obtained by assigning directions to the axioms. There are some intuition and heuristics in doing this. For example, we will prefer to transform linear algebra computation into scalar ones. And sometimes when we encounter tensor product structure during inner product, then we will want to decompose the tensor product. So what about the property of our algorithm? One is soundness, but soundness is obvious because all the writing rules comes from axioms. So the writing always preserve equivalence. And completeness is not that easy. So it can be obtained if you can prove that the writing system is confluent and termination. These are the two main technical contribution of our work. Termination means the writing of a term will have the result that cannot be written anymore. And confluence means if you start using the same term, then all the possible writing traits will result in the same syntax. So we want to prove this, at least for our core language. But this is not easy because we have a term writing system with more than 150 rules, and manually checking them is time-consuming and sometimes impossible. But the good news is we have the local confluence of AC term writing system is decidable. And termination of term writing system, it is not decidable, but we are fortunate. So we use two tools. One is called the SimWrite tool. And to be honest, term writing does not have a very thriving community for now. And this is the only tool that we find can do AC term writing. It is built 20 years ago. But anyway, it works. And it checked that all the critical pairs, meaning all the pair of writings that will diverge, will finally converge. So our system is confluent. And for termination, we use another famous tool called approve. And termination is confirmed by encoding our term writing system into it. So that's the story. We have a core language which covers most of the symbols in Dirac notation, and it is sound and complete. But there is one thing: we don't have big operator. So we further on extend the language with some. There are the syntax for set and syntax for the summation, and we also have the semantical explanation. But the problem is decidability of big operator is not well studied. So our rules are rather heuristic. They are not completeness guarantee, but instead they work very well in practice. So our work conclude in the implementation called Dirac deck. It is written in Mathematica. The reason of choice is we want the language to internally support term writing so that we can write it easily. And also we want there to be a computer algebra system for scalars that can deal with symbols like exponential or trigonometric functions. So Mathematica is the choice. And here is the raw code encoding the earlier example. You can see the first line, it defines the context. We have the operator n with the corresponding type. And the second line defines the maximally entangled state. The third line encodes the equation, and Dirac deck checks the equivalence automatically and confirms the result. That's how it works. We evaluate the implementation on an example benchmark. The examples comes from different sources. They come from the textbook and the CoQ project, which is a foundational formalization, Coq formalization for quantum computation. And we also take some equations as examples from a suitable recent paper. In general, the result is it works well, and the language is expressive, and most encoded examples are solved. To name some applications, the theory and implementation can serve as the solver for theorem provers. For example, if you want to prove equivalence in Coq, then you don't need to manually write all the proof scripts. Or it can serve as a solver, the backend for the verification tools of quantum programs, because you will need to check whether the assertions or the states are equivalent, and they are all written in Dirac notation. And to give you some sense, these are the examples we can do. And for example, and particularly here, the last one, we have the define symbol, meaning here tr trace means the trace of operator. It is not within our original language, but it can be defined using the functions in Mathematica and the Dirac notation we proposed. So the tool can also do some sort of abstract reasoning. And to conclude, you may also be interested in how the work is developed. We write down the rules, and again, there are 150 in total, and many comes from intuition. And we check the termination and confluence using the tool. Thank God we have the tool. And we do the implementation and check the example test suits. Usually there will be counterexamples. For example, critical pairs that will destroy the confluence, or there will be failed tests. So we have to look into the counterexamples and make modification to the rules. So the procedure just repeats again and again. And my feeling is the work is like manufacturing a processor. The only difference is we are using formal method and writing rules instead of hardware circuits. I think this is not a sustainable way. I mean, in the future, we will for sure require the decision procedure for a more complicated language. And by then, managing the rules manually is not a promising way. So can we do it in a better way? Can we find the guidance in the labyrinth in a better way? I think this is the next important question. And my talk ends here. Please tell me your comments or questions. Thank you for your attention.
Okay, we are running a bit behind, but we do have time for one or two questions if we have any.
Yeah, thanks for the talk. You said that this system can be used in Coq to have do automatic proofs rather than having to write them yourself. Is that something that you have actually existing with integration between the tool and like producing some sort of certificate?
Well, that's a very promoting topic, but it's the next story. So in theory, it's possible because the structure of turn writing is very simple, and you can implement it in Coq, or you can extract the writing trace and let Coq check the writing trace. These are possible.
Okay, yeah. So do you envision like essentially re-implementing the whole system inside Coq, or is there some way to get fast plus certificate?
Yeah, I'm working on a next generation of Dirac deck, which is written in C++ and emphasize on speed and efficiency. And also, we did some exploration to integrate it in Coq, but the difficulty is if you want high efficiency, then you have to do some optimization, and you have to let Coq also check this optimization. This can be quite hard.
Okay, we have one last question from Matthew.
Hi, thanks for the talk. Really interesting. So I had a question about your syntax. Your syntax had a lot of different cases. It resembled like a concrete syntax instead of an abstract syntax. I imagine this is so that you can actually kind of finely tune the direction of the rewrite rules. But have you thought about kind of a simplified syntax, like either an abstract syntax and kind of giving the rules on the abstract syntax, or maybe like a typed syntax that kind of simplifies this thing a little bit?
Exactly. But here is the trade-off. So we stick with the concrete syntax because we want to use the naive term writing. Because naive term writing can be checked by the tools, and we get the nice properties. If you can also design the abstract syntax, but then you will need the type system and type checker, and there are some term writing rule will invoke the type checker, so the whole system will not be machine checkable. That's a problem.
Right. Yeah. Okay. Thanks. Perfect.
Great. Let's thank the speaker one last time.